then c equals root, right, because you have a squared plus b squared equals c squared. You take the square root of c, you take the square root of the other side. C equals a squared plus b squared, but b is a plus 1. So you have a squared plus a plus 1 squared equals the square root of 2a squared plus 2a plus 1. So it's important you get that definition, and that you see that this is like, this is a consecutive Pythagorean triplet. This is like the definition. So essentially, that's cool. We know how to define one. But the question is, how do we go from 3, 4, and 5 to 20, 21, 29? And how do we go to 119, 120? How do we go from 20 to 21 to 29 to this, and then this to the next one, and the following ones? How do we get like the next triplet? And is there an infinite amount of these triplets? So basically, back when I was in grade 8, I had kind of an advanced math teacher come in, and he would, he'd teach us kind of cool things. He taught us how to convert bases, or tried to teach us how to convert bases back in grade 8 and stuff, and he always kind of had a cool problem. So one time he came in and put this up on the board, and he's like, he asked the grade 8 class, like, how do you go from 3, 4, and 5 to this and this? And so we're all kids, and we don't know like too much math, but we experiment, we play a little bit, and we notice a peculiar pattern that's kind of emerged between the triplets. So you have 20, this number right here, is equal to 2 times 3 plus 4 plus 2 times 5. So this is just going back to the previous triplet. And we notice, okay, well let's apply that algorithm to the next one. 119 is equal to 2 times 20 plus 21 plus 2 times 29. And you get this number right here. So we're like, okay, and we tried it for the next maybe 5, 10 cases, and it works. So we thought, okay, this works. And at a grade 8 level, we thought, well, okay, so what? Like, it worked for the first 20 cases. We didn't know too much. We didn't know a lot of math or how to prove this, per se. So I heard about the talk coming up, and I was like, well, like, this was influential to me. So I thought, well, how can I prove this, and how can I make it so that I can tell you with certainty that this is the link? And so this is where it gets a little bit more mathematical, and I'm going to try and go slow so you can follow me and see what I'm doing. So essentially, you go down the list, dot, 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 you have AI, BI, CI. The ith, this length, the ith term of this length, the arbitrary, and the ith of this. So this would be A1, A2, A3. Or sorry, A1, B1, C1, A2, B2, C2, the next one, A3, B3, C3. So that's how we're like denoting the triplets. So if I were to write it here, it would be like AI, BI, CI. That term in the sequence of triplets. So we found that the length was 2 times 3 plus 4 plus 2 times 5. So writing it a little bit more, like denoting it in these terms, we have an plus 1, because this is, say this is a, n, b, n, c, n, like arbitrarily. Then we have an plus 1, this is our hypothesis, is equal to 2an plus bn, but bn is just equal to an plus 1 plus 2 times cn. And so, okay, but we know what cn is equal to based on our definition that we go back to, that c is equal to this right here. And we know that if this is a triplet, then a and c must be natural numbers or positive integers. So we defined an plus 1 as 3an plus 2 root this, 2an squared plus 2an plus 1 plus 1. And this is by substituting in the cn. So we come up with a proposition. We say if an plus 1 cn is a consecutive Pythagorean triplet, and I want to denote this as star, and an plus 1 is equal to this. So we're saying basically, we have a triplet here, we have an plus 1, and an plus 1, it's true that an plus 1 is equal to this, what I've hypothesized here. Then an plus 1, the next Pythagorean triplet, is also going to be a consecutive Pythagorean triplet. So we've come up with a hypothesis. We've said, if it's true that an plus 1 is equal to this, then the next term is also a consecutive Pythagorean triplet. It's important to understand the hypothesis, so where we go to the proof, and I try to use induction to prove it, which I actually just learned in my formal logic math course. So it's important to note we have a very important tool here. So remember in the proposition we said if an plus 1, Cn is a consecutive Pythagorean triplet. So that's essentially one of our assumptions that we made. But what do we know is true if an plus 1 and Cn is a consecutive Pythagorean triplet? We go back here and we get that this expression right here, 2a squared plus 2a plus 1, is a natural number. We've assumed that that part of the link is true. We assume that this is true and we want to show that this is true. So this right here is going to be our biggest tool, that this is a natural number. So, you know, in induction, you need a base case, and obviously it's very simple here. 3 squared plus 4 squared is 5 squared. So that's kind of where we start. So okay, then we go move to our inductive case, and we want to show that if Cn plus 1 is equal to this, right? Because we're going back to this definition. We're changing it now so that it's an plus 1. So we say, if Cn plus 1 is equal to this, then an plus 1 and Cn plus 1 must be natural numbers, right? Because this, we have Cn plus 1 is equal to a squared, an plus 1 squared plus bn plus 1 squared. So n plus 1 is denoting the n plus 1 term. From back here, remember how we simplified that? We had a squared plus a plus 1 squared. Same thing here. If Cn plus 1 is equal to this, then an plus 1 and Cn plus 1 must be positive integers. So, the first thing we need to show, right? We have two things, essentially, that we need to show for this proof. We need to show that a and c are both natural numbers. If we can show that, then we can show that the link exists. That if you have a and n plus 1 and Cn, you apply this formula, you get an plus 1, the n plus 1 term, the an plus 1 plus 1, and Cn, we show that it must be a triplet. So the first thing we need to show is that an plus 1 is a natural number. So we have an plus 1, and I simplified it here, right? This is star, is equal to 3an. So we know that 3 times a natural number. We've assumed that the nth one, we've assumed that an and Cn are natural numbers. So we have 3an, this is a natural number. This big thing right here, this is a natural number. And 1 obviously, actually this is the important step, that this is a natural number. Because this is what we assumed, this is our biggest tool right here, is that this, by assuming the nth case, we've said that this right here is a natural number. So we have a natural number, plus 2 times a natural number, plus 1 is a natural number. So we know that an plus 1 is a natural number. So that's the first part of our proof. We can check off that a is a natural number. That's the first part. But now we need to show that Cn plus 1 is also a natural number. And so this is a little bit more challenging. We know that Cn plus 1, if it's a triplet, is equal to 2an plus 1 squared plus 2an plus 1 plus 1. And that's just by the definition of Cn plus 1 is equal to, as you know, an plus 1 squared plus bn plus 1 squared. If you have the hypotenuse, you take the square root of the square, the sum of the squares of the side lengths, and you get the hypotenuse. We substitute bn plus 1, obviously, is an plus 1 plus 1 squared. You simplify it, you get this expression. So this is what Cn plus 1 is. And we want to show that this right here is a natural number. If we can show that that's a natural number, then we've shown that both a and c are natural numbers, and so the next triplet must be a natural number. So things get a little bit long here, and I wrote this down, and I don't expect you to really pay attention to much of the algebra. We have an plus 1 in this expression, but I've already told you what an plus 1 we've hypothesized is equal to. It's equal to this. So have fun substituting that in the square root. That's what I thought to myself. And so you substitute it in, you get this big, long, horrible expression. And I kind of got to this step in my proof, and I was thinking, well, that sucks. That doesn't look like a square root of anything. And it's a little bit like, I don't have enough time in this talk to talk about it, but using something else, I just kind of an ad hoc approach mostly, guessing and checking. It turns out that this big thing inside the square root is just this squared. You can factor this expression, this big, long, horrible thing, into one little thing here squared. and that's it. So obviously you've got the square root of this expression squared, and you cancel out the square root and the square, that's obvious, and you get 4 equals, so Cn plus 1, right, we're going down, is equal to 4an plus 3 times this squared plus 2. So now how do we check it's a natural number? Well, we've assumed the nth case is true, an is a natural number, but by also assuming the nth case is true, remember our biggest tool? This is a natural number. So this is a really nice tool that we have. Plus 3 times a natural number, so natural number, 2 is a natural number. This is by our assumption, of course, the nth case. In induction, we assume the nth case, we get the n plus first case. Cn plus 1, natural, so Cn plus 1 is a natural number. You guys all know that. Yes?
How do you know that statement under the square root is a natural number? Like that's what square root, no, like you say by assumption, square root of 2an squared plus 2an
right.
plus 1.
And that's because we've assumed that the nth, right? Because, alright, this is very important. So,
is it so you've chosen, your assumption is that you've chosen some an so such that that's
right, we've assumed, so we have ai, bi, and ci. ai plus 1, bi plus 1, and ci plus 1, right? This is the next one. So we're assuming if we have a triplet, so right, this can be rewritten as ai plus 1, and ci is equal to this square root right here. So we assume, I'm not going to write it all down, but you know, it's equal to this. If this is a Pythagorean triplet, right? So by definition,